Welcome to another maths problem solving video. Today we'll be looking into the cricket jump problem or the cricket hop problem. So what exactly is this problem? So I have a cricket with 4 leaves on a lake. A cricket is already on one of those 4 leaves, and let's see what happens after that. A cricket randomly hops between the 4 leaves, on each turn hopping to one of the other 3 leaves with equal probability, which means there's an equal chance of hopping into any of those 3. After 4 hops, what is the probability that the cricket has returned to the leaf where it started? So this is your puzzle. This is the cricket hop problem or the cricket jump problem. Now, as you already are familiar, these are non-routine math problems. There is no straightforward formulas that you can just apply and get it done with in a routine manner. It's non-routine precisely because there is a complete absence of any formula that can be applied. And in fact, this is an application problem where you need to think through the problem, define the problem, and then take it forward. So if you are stumped of not knowing exactly how to proceed, that is precisely the perspective with which I've created this particular video to help you solve it, not just help you know the solution. So let's get started. Step number 1 for me is nomenclature. Nomenclature means naming the problem space so that it's a little easier to create a language around it, create the semantics around it. So the leaf where the cricket already is, I'm going to call it A. The remaining, I'm going to call it B, C, D. How does it help me? So first, let's understand what the problem is asking us to find out. It's asking us to find out the probability. The probability is nothing but the ratio of the number of ways in which a favorable outcome happens to the number of total possible outcomes. That's it. It is just a mathematical language that expresses this element of chance. So we want the cricket to come back to A. How many different ways can it do? Can it come back to A after 4 jumps? That would be favorable. And all the possible places it can land after 4 jumps would be the number possible. So let's get started. So we know that it starts off with A, which means he can go to B, C, or D. And let's say he lands at B after the first jump, which means after the second jump, he can go back to A or he can go to C or D, but of course he can't stay back in D. Now, what I've boxed there is kind of a repeating pattern, as you can see. So B leads to 3 things, C leads to 3 things, D leads to C 3 things, right? So this is a kind of like a fractal design, and it's going to keep going further. So for instance, if you were to take the path A, C, B, like he starts from A, jumps to C, and then goes to B. And there, again, the same fractal design will come because from B, he'll be able to go to A, C, or D. Okay, so this is the repetitive design. But however, if you have to do 4 jumps, you would have to create a lot of arrows because after 1 jump, you need 3 arrows. After 2 jumps, you will need 3 plus 9, 12 arrows to be drawn. After 4 jumps, you can calculate how many that is. But it's going to be quite a lot, right? It's going to be quite a lot for you to create all of those jumps, right? If you're interested in the answer, then it's about 120 different arrows that you need to create. And of course, you don't have the time or the space to actually do it. And this is where pattern recognition helps you. So what I'm going to do is to think of this more as an experiment. I'm a scientist who's just noting down this cricket jumping from one leaf to another and then list down the number of possible paths. So after the first hop, I know that there's 3 possible paths, which is AB, AC, and AD. So that's 3 possible. After 2 jumps, I know that there are 9 possible paths, which means it's ACB, ACD, ACA, ADA, ABA, ADC. You can imagine, right? Like you can just follow the arrows, and wherever there is the endpoint, that particular path would become the path of possibility. Now, if you were to extend it to 3 jumps, you can imagine that each of those endpoints, there are 9 endpoints, and the fractal design is such that each of these 9 endpoints will bring 3 more, therefore making it 27. And then after 3 hops, there'll be 27 endpoints, which means after 4 hops, there'll be 81 endpoints. So in total, there are going to be 81 possible paths that the cricket can take. But how many of this is favorable for us? So let's understand the same way. Favorable is when he ends up back in A. Now imagine jumping back to A after 1 hop. Favorable path is 0. There's absolutely no chance of going back to A. But after 2 jumps, he can definitely get back. In a sense, it could be ABA, ACA, ADA, the 3 ways in which he can get back to A. After 3 hops, it's possible to do it in 6 different ways, because discounting all the endpoints which are already at A after 2 hops, every other one is definitely going to lead to another A, which means, let's say he starts off from A, he goes to C, and then he goes to B. There's a possibility of getting back to A. That's one of the possibilities. So similarly, there'll be 6 possibilities. Extending the same logic, you can look at all the different ways. There are 27 endpoints after level 3, after 3 hops, out of which 21 would be non-A and 6 would be A. Because remember, those were the 6 favorable paths after level 3, after 3 hops. Which means the non-favorable ones would be 21, and those would be the potential to become favorable after 4 hops. So therefore 21 would be the favorable path. Now you can calculate the probability in a very similar fashion. After 1 jump, the probability that you end up in A is 0. After 2 jumps, the probability that you'll end up in A is nothing but the favorable path divided by the possible path. So 3 by 9, which is 1 by 3. After 3 hops, it's 6 by 27. After 4 hops, it's 21 by 81, which is the same as 7 by 27. So that's the probability of it. I hope this particular problem solving method was helpful. Tabulating it, thinking like a scientist, thinking of the whole math problem as an experiment, looking for patterns and therefore trying to solve it. So what are the lessons learned? Nomenclature is a key aspect of problem definitions. Many a non-routine problem can be solved if you can find the right nomenclature and define the problem in a very proper, precise manner. Modify the parameters of the problem, which means we didn't wait and directly look at 4 jumps. We said, hey, what if it's 1 jump? What if it's 2 hops? What if it's 3 hops? And then we came to the 4th hop, right? So there is no, absolute dictum saying that you just got to take the problem at its complete word and say that there's only 4 possible jumps, right? You could always modify it and say, what's the probability for 3 jumps? What's the probability of landing on A after 2 jumps? In other words, solve for simpler parameters and you'll be able to understand the underlying pattern, which will help you solve it for more complex ones. And always look for patterns, fractals, patterns. This is the heart, the lifeblood of mathematics. So if you look at patterns and if you can nomenclate those patterns, it becomes very, very easy to extrapolate those patterns into larger, complicated numbers or designs. I hope you found this useful. If so, please share, like the video, click on the bell icon, and I look forward to seeing you in the next video. Thank you.